Okay, this will be the last example that we are going to solve by using the moment distribution method. Now here we have a frame structure and we have two pin supports, so there is no sway. It doesn't move, it doesn't translate. We have a cantilever here with a point load 20 kN, a uniformly distributed load, and I have a support settlement at point A. So again, let's start our solution with the discretization. We will divide the structure into smaller pieces and we will try to figure out how it behaves. So here, I really don't worry about the loads right now. All I worry about how this structure behave. I have a node here, member AB, node B, member BC, node C, and member CE, and member BD and node D. So what do we know about this structure? So here at this point is free to rotate, meaning that I can use modified equation for this one. So I don't have to define any rotational degrees of freedom at point A. At point B, I have a rotational degrees of freedom, theta B. Member BC, let's take a look at point C. Yes, I have a cantilever here, but without the loading, I know that this point C is also free to rotate. So I can also use modified equations for member BC. So basically, after the discretization, I can say that I got only 1 degrees of freedom, which is rotation at B. So I will do moment distribution only at point B. The main difference of this problem from the previous problems is at point B, I have three members joining to point B. So I have to distribute whatever the moment I have, the unbalanced moment at B, to these three members. So once we do the discretization, next step is the stiffness factors. So let's calculate them. Let me erase this part. Okay. Stiffness factors. So I need the stiffness factor of member AB. So K AB, I decided to use modified stiffness factor for it. So it's equal to 3EI divided by 6. Member BC, KBC, again we decide to use the modified equation. So that's equal to 3EI over 8. And finally, our final member is member BD. That's equal to 4EI over 4. So I don't need to write down the stiffness factor for member CE because it's a cantilever and I know that it doesn't show any resistance to rotation. Now, next step is calculate the distribution factor. Okay, let's calculate that. So distribution factor BA is equal to stiffness factor of AB, 3EI over 6 divided by the total stiffness at point B. I got 3 members joining to B, so I should have 3 stiffness factors. So 3 over 6 plus 3 over 8 plus 4 over 4, write it this way, EI. So this gives me the stiffness factor as equal to 0.267. So this is basically, this tells me that member BA will carry the 26.7% of the moment. So distribution factor BC is equal to 3/8 EI divided by, the total stiffness is the same, 3/8 plus 4/4 EI, and that's equal to 0.2 point here, and distribution factor BD is equal to 1 minus 0.267 plus 0.2, and that's equal to 0.533. So these are the distribution factors. As we can guess, the member BD is the strongest member, and thus it carries the 53% of the moments. Now, the next step is calculate what happens when there is no rotation, when the rotation at P equal to 0. Okay, so we do it by saying the fixed end moments and moments now. Let's take a look at member AB now. So pin here, pin fixed, and we know that this point move in the downward direction. So in that case, that will be the court rotation, the phi angle, and phi angle is equal to, it's in the counterclockwise direction. So 0.01 is the amount of settlement divided by the length, which is equal to 6. That's the phi angle. So the fixed end moment, the moment that will be created at this end, is, let's call it fixed end moment BA, and that will be equal to, I will be using the slope deflection equation for that. Fixed end moment BA is equal to modified equation 3 EI divided by 6 multiplied by the phi angle itself, so minus 0.01 divided by 6. So the result is equal to minus 50 kilonewton meters. I put 60,000, EI is 60,000, so I put 60,000 instead of EI, and I obtain 50,000 kilonewton meters, and this minus signs tell me that I have a clockwise moment. So we handled member AB. At member BC, I have a uniformly distributed load. Magnitude is 12 kilonewton meters. So the fixed end moments are as follows. This is 96 kilonewton meters. I make a mistake. Let me correct it. I don't have fixed support here, but I should have a pin support because I decided to use modified equations. So I obtain 96 kilonewton meters by using WL square over 12. I have node C here, and I show it this way because it doesn't matter if it's fixed or flexible, and the moment is always the same. If this is 20, so the moment that I see at this end will be equal to 60 kilonewton meters. So this is what I see when the rotation at B equal to 0, no deformation case. I have a fixed moment here due to the settlement, and I can calculate that moment by using the slope deflection equations. I have a uniformly distributed load on member BC, and remember that since point C is free to rotate, I use the modified equation here and calculate 96 kilonewton meters. And this cantilever is actually transfers a moment to node C, and the magnitude of moment is 60 kilonewton meters, and we learned how to handle that moment before. Now we can start the moment distribution, and in order to do that I will erase this part and do the moment distribution right here so that we can see all the information in a single page. So I will draw my table. Now the table drawing is a little bit tricky because we have three members joining to node B. In other words, I will have three distributions here and carryover moment. So the way I'll draw it is as follows. You can draw the way you want, any way you want. Let me write it right here. So this is point A. I got point B here. C, E, and I'll just show D in here. That's D. So let me show the distribution factors first. So this is dF at point A. This is 1.0. So I will divide B into three columns. So the distribution factor here is 0.267. So distribution factor for this part, I'll put a note to myself. This column is BD. So 0.533 here. And this distribution factor is 0.2. Let me move point C to a little bit right. So C in here. So the distribution factor at point C is I got 1. All the moment will be carried by member BC. This is 0. So I got point E here. And point D, I have a fixed support. So this is equal to 0.0. And again, let me put myself a note that this represents the distribution factor for dB. So that's the picture. These are the distribution factors. So let's write the fixed end moments. Sorry, it's very difficult to write with this thing. So F dot E dot M fixed end moment. So the fixed end moment BA is minus 50. I don't have any loading on BD. The fixed end moment BC is 96. So let's put it here. And at the end of the cantilever, I got 60. So let's show it right here. So this is the case when there is no deformation. Now, what do we do first is we first handle this 60 kilonewtons. So I'm releasing node C first. Okay. So distributed moment C. So here release C. This is what I'm doing. When I release C, the node C rotates, and due to that rotation, I see an equal but opposite moment at the end of member BC, and point C rotated, and due to that rotation I will have a carryover moment that's equal to minus 30. So I'm done with node C. Now node C in its equilibrium, and the final moments are 60 and minus 60. Now I need to handle node B. So let's take a look at node B. Due to the support settlement I got minus 50. Due to the rotation at C I got minus 30. And due to the uniformly distributed load I got 96. So unbalanced moment at node C is equal to 16 kilonewton meters. And this 16 will be resisted by member BA, BC, and BD. So distributed moment at B, I got 16 unbalanced moment, multiply it with the distribution factor. This is minus 4.27. Multiply 16 by 0.533, I got minus 8.53, and multiply it by 0.2, I got minus 3.2. So these are the distributed moments due to rotation at B. Now carryover moments. No carryover to A, no carryover to C, but I will have a carryover moment to node D, and that will be the half of 8.53, which is minus 4.26. So this is the final step. Now all the nodes are in equilibrium, and I can obtain the final moments, which are as follows: 0, minus 54.27, minus 8.53. Here I got 62.8, minus 60 plus 60, and minus 4.26. So these are the final moments. Let's draw the free body diagram. So let me erase this part, and I will show you the free body diagram now. So this part is erased. Let's draw it. Uniform distributed load, a point load here, and the support settlement that's equal to 1 centimeters. So BC minus 54.27, it's a clockwise moment. 54.27. Now moment BD is minus 8.53, so another clockwise moment. So this is 8.53. At the end of member BD, a clockwise moment of 4.26. 4.26. At the end of member BC, a counterclockwise moment 62.8. So this is equal to clockwise 60 and counterclockwise 60. So this is the free body diagram. Now by using that we can draw the moment diagram. So the moment diagram will look like this: the sign convention plus So these are the directions that I choose to be positive. So that's point C. That's A, B, and D. So I have a negative moment at the end of member AB. There is no loading, there will be a linear variation. This is minus. So at member BC, both ends has negative moments. So we see a parabolic variation, minus, plus, minus, and the linear variation at the cantilever, minus. Of course, these 2 points are not at the same point, so that's another, I have to be careful while doing that because they don't go to the same moment value. So let's draw it this way, minus, and the moment for member BD can be drawn as follows. At the top, I have a negative moment if member BD goes from bottom to top. At the bottom, I have a positive moment. So let's draw it this way. This is plus, this is negative, this is 4 point minus 26 minus 8.53, and you can put the other values. So the only challenge here is the support settlement, but remember that if we, as a starting point, we assume that rotation is equal to 0, and we can actually calculate the moment due to any deformation by using the slope deflection equations, and this is what we did. For a 1 centimeter support settlement, we calculated the moment to be equal to 50. The other challenge is how to handle this 20 kilonewton. Since this is a determinant, CE is a determinate moment, I know the end moment here, which is equal to 60. And I did distribution just once at this node. And the equilibrium condition should tell me that I should have the same moment, but the opposite side, minus 60. And due to that 20 kilonewton, there will be a rotation. And this rotation will be caused by a moment whose magnitude is minus 60. So we know that at the fixed end, far end, it will create a moment that's equal to minus 30. So we are done with the effect of this 20 kilonewton. We calculate the fixed end moment due to 12 kilonewton meters. And the only difference of this problem from the previous ones is at point B, I have 3 members. So I drew 3 columns underneath point B. This part represents the BA part, this is BC part, and of course I cannot draw D side by side to point B, so I draw it here and put a reminder to myself so that whatever the moment I see, the carryover moment will go to point D. So that's why I have 8.53 here, and I moved a half of it to the last column, 4.26. So that finalizes our discussion on the moment distribution method. Our next class will be on the derivation of the stiffness method.